All right, let's jump right in. We're about to explore this incredible, invisible force. It's been a part of our planet since day one. And today, it powers everything from cutting-edge cancer medicine to deep space exploration. We are, of course, talking about radioactivity. So here's a good question to start with. What could possibly link cancer therapy, ancient artifacts, and the smoke detector in your house? It kind of sounds like a riddle, right? Well, the answer is a fundamental process of nature, radioactivity. It's this surprisingly versatile tool, and today we're going to break down how it all works, from the spontaneous decay happening right under our feet to the man-made atoms that are at the very heart of modern technology. Okay, so let's get to the core of it. What is radioactivity? Well, it's all about stability. I want you to imagine an atomic nucleus as a really wobbly tower. It's got too much energy, or maybe the number of protons and neutrons is just out of whack. To keep from falling over, it has to get rid of something. It has to shed a piece. That piece is what we call radiation, and the whole process is radioactive decay. Simple as that. So first up, let's talk about the radioactivity that's always been here. This is the natural, spontaneous stuff that's happening in elements all around us. Think of it like a constant, low-level hum of atomic transformation that started long, long before any of us were around. So what's the actual difference between a stable nucleus and an unstable one? Well, think of it this way. Stable nuclei have found their happy place, a perfect balance of protons and neutrons. They'll just stay that way forever, unless something really dramatic happens. But unstable nuclei, they've got too much of something. Too many particles, or just way too much energy. This imbalance means they're destined to change, and they're going to do it all on their own. One of the main ways a heavy nucleus can slim down is through something called alpha decay. It's kind of like throwing a prepackaged bundle right out the door. And this bundle, the alpha particle, is actually just the nucleus of a helium atom, 2 protons and 2 neutrons. So when a big atom like uranium does this, it doesn't just lose a little weight, it literally transforms into a completely new, slightly lighter element. Next up, we have beta decay, which is more like an internal makeover. An atom with too many neutrons can pull off this really clever trick. It flips one of its neutrons into a proton. Now, to keep everything electrically balanced, it has to spit out a high-energy electron. That's our beta particle. The atom's mass barely changes at all. But now, with one extra proton, bam, it's a totally different element. It's actually moved one step up on the periodic table. And then you've got gamma decay. This one's a little different. It often happens right after an alpha or beta decay. The nucleus has already changed, but it's still a little too energetic, like it's vibrating with excitement. To calm down, it releases this final burst of pure energy as a high-energy photon, which we call a gamma ray. The element doesn't change this time. The nucleus is just releasing its leftover energy and finally settling into a more stable, relaxed state. This old diagram here is just a fantastic illustration of this whole idea. You can actually see how early scientists were mapping this all out. They're showing a single element, radium, going through this whole chain of transformations, spitting out those alpha and beta particles we just talked about, on its journey to becoming stable. This is what's known as a decay chain. It's like a cascade of instability, but with a stable destination at the end. Now, for decades, radioactivity was just something we found in nature, something we observed. But then came this revolutionary idea. What if we could make things radioactive? This is where we move to that breakthrough moment, where humanity went from just being an observer to actually being a creator. And the pace of discovery here was just breathtaking. So in 1896, Henri Becquerel literally stumbles upon natural radioactivity by accident. A few years later, Rutherford and Soddy have this incredible insight that atoms are actually transforming into other atoms. But the real game changer? That came in 1934 from Irene Joliot-Curie, Marie Curie's daughter, and her husband, Frederick. This was the lightning bolt moment. The Joliot-Curies were bombarding just ordinary, stable aluminum foil with alpha particles, and they noticed something that was just unbelievable. Even after they took their radioactive source away, the aluminum itself kept emitting radiation. They hadn't just observed radioactivity, they had created it. They had turned a stable, everyday element into a brand new, man-made radioactive one. And that brings us to this really crucial distinction. Natural radioactivity is spontaneous. It just happens, all on its own, in certain heavy elements that have been around forever. But artificial or induced radioactivity, that's all us.
It's the process of taking a perfectly stable nucleus and making it unstable, usually by smacking it with a particle like a neutron or a proton.
This discovery, the ability to create radioactivity on demand, completely blew the doors open for science and technology. This is where all that theory turns into incredible technology that reshapes everything from medicine to how we understand our own ancient history. So get this, since that incredible discovery in 1934, scientists have created over 2,000 different artificial radioisotopes. We now have this massive toolkit of custom-made atoms, each with its own unique properties that we can put to work in all sorts of amazing ways. So, how do we actually make them? Well, we basically have two main tools in our toolbox. We can use nuclear reactors to flood materials with neutrons, creating isotopes like cobalt-60, which is an absolute workhorse for radiation therapy and sterilizing medical gear. Or we can use particle accelerators called cyclotrons. These use protons to create other isotopes, like the fluorine-18 that's absolutely essential for the PET scans that doctors use to find cancer.
And the impact on medicine has just been enormous. Just try to wrap your head around this number. Worldwide, there are over 50 million nuclear medicine procedures performed every single year. That's 50 million times these custom-made atoms are used to diagnose and treat diseases. It's just staggering. But these applications go way beyond the hospital. In factories, radioisotopes are used in gauges to make sure that paper or plastic wrap is the absolute perfect thickness. They help geologists find oil deposits miles underground and find tiny, hidden flaws in critical pipelines. And hey, remember that smoke detector from the beginning? A teeny tiny amount of a radioactive isotope creates a steady electric current inside. The second that smoke particles interrupt that current, the alarm goes off. It's just brilliant physics protecting your home. Radioactivity also acts as our planet's most reliable clock. The steady, predictable decay of carbon-14 lets archaeologists state things like ancient bones or fabrics, and on a much, much grander scale, the slow decay of uranium into lead inside of rocks lets geologists measure the age of minerals that are billions of years old, which is how we know the age of the Earth itself. So think about that journey. We've gone from a strange, shadowy image on a photographic plate to a fundamental force of nature that we can create and control with incredible precision. It's a process that reveals the past, diagnoses the present, and even powers our journey into the future. It really just leaves one question, right? What are we going to ask the atom to do for us next?